All right, so for this one, I'm going to take what I've drawn at an angle representing our actual lab setup, and I basically rotated the axes, okay? So that now I'm basically treating the surface as my horizontal, okay? That's going to make the mathematics a little more straightforward. So we're just going to treat it in this nature. Now, the weird thing is, because I basically rotated the axes here, that puts our force of gravity on an angle. Okay, it is still the same setup as over here. I've essentially just rotated everything to make this surface the x-axis. Okay, so that's what we have here. Okay, so if I kind of draw this as a free body diagram now, you see that I essentially have the force of gravity acting on an angle. Okay, that's only true for this diagram. It's actually pulling straight down, but I've rotated the diagram, so now it's on an angle. And I can see some component forces now. I have the force of gravity in the y that's opposing the normal force, and those should balance because it's not going to accelerate up or down off the surface. And then horizontally, I actually have this component right here, okay? That is equal to the push force, okay? This force right here is basically what's pushing my cart down the track, and opposing that is my force of kinetic friction, that F sub K, okay? Now, that net force, because I expect that this force is going to be larger than this force, that net force will be set equivalent to mass times acceleration by Newton's second law. Okay, now I'm going to break down the components a little bit even further, okay? So what I've looked at is the cosine of my angle, okay? Because the cosine is adjacent over hypotenuse, basically the cosine of my angle is my force of gravity in the y divided by my force of gravity, which is actually the hypotenuse, the way this is set up. So I can also rearrange my terms here and say that my force of gravity in the y is equal to the force of gravity cosine theta, and that this also, if I substitute my force of gravity for mass times gravity, because that's what the force of gravity always is equal to, this whole thing, Fg in the y, is equivalent to mass times gravity cosine theta. Okay, so that's the important part for this setup. Okay, the next part, we're looking at the vertical component. Okay, well, actually, this is going to be a horizontal component. A sine theta, usually we see that as a vertical component, but for this, the way the geometry works out, because my force of gravity in the x is actually opposite of my angle, that's going to be a sine function this time. So sine theta equals Fg in the x over Fg, okay, opposite over hypotenuse, okay? Rearrange my terms, Fg in the x equals Fg sine theta, or mg sine theta. So that tells me my force of gravity in the x is equivalent to mass times gravity times sine of theta. Okay, I've just done some trigonometry and solved for what my component forces are, Fg in the x, Fg in the y. Last portion of this down here, I'm now looking at the net force in both axes, and this is going to be important because ultimately this is what's going to dictate the motion. Okay, so my net force in the x, that's where I'm going to accelerate, because that again is the surface of my track, and I'm going to be accelerating downward. Okay, so because of that, my force of gravity in the x, which just so happens to be equal to mg sine theta, you could plug that in, and minus my force of kinetic friction, which we know the equation for kinetic friction is mu k times the normal force, okay, we're going to get an equation for the normal force here soon, is equal to our overall mass times our acceleration. So that is showing how all these component forces in the x sum to mass times acceleration. That has to be true by Newton's second law. Okay, and then on the y-axis, we have the normal force pushing up, okay, and then the force of gravity in the y going down. Those should balance to zero, okay, because I'm not going to be accelerating up or down off the track. It's not going to come off the track. It's not going to go through the track. So that in the vertical direction, my net force should be zero because I should be in equilibrium in that direction. That means that my normal force is also equivalent to the force of gravity in the y direction. That's all going to be very useful when you start doing your mathematics. I'm also going to draw out these equations on the assignment sheet, so you don't have to memorize this off the video. I'm just showing you the derivation for where everything came from.